Okay, welcome back. So we're going to derive the formula for adding up the first n terms of an arithmetic sequence. And so this is a technique that comes up that's very useful, that's used in different cases. And this is just one of them when we're developing formulas involving sequences. So what we can do is, it's a really neat trick. Because what we could do is we could take a sum, a partial sum, and we can order the terms from the first term to the last term, and that's going to add up to S of n. But we can also order them the other way, starting with S of n, the last term, and working our way to the first term. Okay? And so what happens is, if we just add these two equations down, we get 2 times S of n is then equal to what? It's going to be a1 plus a sub n plus a2 plus a sub n minus 1 plus a3 plus a sub n minus 2 all the way to a sub n plus 1. So now, what do we do with this? Well, if we look, oops, hold on, not 1. A sub 1. So we've got a sub 1 here plus a sub n. And we've got a sub n plus 1 over here. And then if we work in, we're going to have another a sub 2 plus a sub n minus 1. Right? So these are going to pair up from the inside out. And the thing is these are going to add up to the same value. And so to see it, let's just do an example of, let's just take a really simple example of 1, 2, 3, 4, 5, 6, right? And we could take 6, 5, 4, 3, 2, 1, right? So we're just adding those both ways. And so these are all going to add up to 7. Right? And so what this ends up being is what? If I take the first term plus the last term and take n divided by 2. And in this case, n is equal to 6, right? And so 6 divided by 2 is 3, so 3 times 7 is equal to 21. And so if you notice here, this equals 42. But remember, this is equal to 2 times s sub n. So you have to divide by 2, which gives us the 21. So in this case here, what we're going to have is, well, how many of these pairs are we going to have? In this case, we're going to have n of them, right? Because we have n terms. And since these are going to be the same, we can just represent it by the first term and the last term. Okay? So this is an example, but an example is not a proof. So we can see that it works. But how are we going to see it here? Well, if we do this, oh, you know what? Here. Let's go back. Let's go back here instead of trying to do it all there. Let's go back to here. Yeah, let's rewrite these in terms of the common difference. So A1 plus D plus, so we'll do this one, and then A1 plus 2 times D all the way to A1 plus and this would be, the bottom one would be how do I want to do that? Yeah, if I'm going to start here, then to go down to the bottom, instead of adding D, I'll subtract D. So this will be AN minus D to get the next one, right? So I'll start with A sub n. I'll subtract the common difference to get to the next one, plus A sub n minus 2D to get to the next one, all the way to A sub n minus n times d to get to the first one. Now, if I define it this way with the common difference, now you see when I add, I get 2 s sub n and it'll be a1 plus a sub n plus, now notice when I add down, the d's cancel and I get a1 plus a sub n. And again here the 2d cancels with the negative 2d and I get a sub 1 plus a sub n. And then this happens all the way to the very last one. And so again, because I have n terms, I end up with n of the same thing, which is going to give me n times a1 plus a sub n. And then of course, this is equal to 2 times s sub n. So all I have to do is divide both sides by 2, and I get the formula. Okay, so you have to do a little bit of algebraic manipulation to make it work, but you do an example and you say, okay, I know what the goal is. I know these all have to be the same. When I add them up, I have to get the same term because it works in the examples. But if I want to prove that this works for all of them, I have to show that it happens in the general case. So I had to rewrite all of these using D. So because I needed everything in terms of a sub 1, a sub n, and this was the only way to do it. Have a great day.